How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at heterogeneous equilibria practice problems. So our objectives will be to accurately set up the equilibrium constant expression and calculate its value for heterogeneous equilibrium, including saturated solutions. All right, that's the other word there. All right, so 15.4, number one. The equilibrium constant expression does not include pure blank or pure blank, pure solids or pure liquids, right? So whenever we're writing the expression, if it's, hey, solid, you're not including it. Hey, here's a liquid, not including it. All right. Yeah. Number two, what is the correct equilibrium constant expression for this? All right, well, let's see. We'd say KEQ equals concentration of the product. So I got an H plus over there. That is aqueous. We have an HCO3 minus, which is also aqueous. Coefficients are 1. All over the reactants, well, let's see. There's a pure solid there, so that's not going to be involved. There's also a pure liquid there, not going to be involved. So this is it. That's it. It's heterogeneous because we have different phases. Hetero means different, and that's what we got going on. Number three, the Kp for the reaction that follows is blank. So again, all right, Kp is going to be terms in pressure instead of concentration. The pressure of the products, well, we have CO2, the coefficient of 1. So that's boom. Times, well, let's see. Solid, nope, not going to be a part of it. Hey, another gas. All right, so the pressure of H2O, but it gets squared because of that coefficient of 2. Over the reactants. Well, let's see. CuO solid, not going to be a part of it. But CH4 gas will be. So the pressure of CH4 and its coefficient is 1. So we just leave it as that. That is the expression. Number four, the solubility of CeIO4 is this many grams per 100 milliliters. What is the KSP? So the KSP is solubility product. So it's nothing special. It's just a KEQ for a solution for salt dissolving. So we start with CeIO4 and it dissolves to give us Ce plus 4 and 4 IO4 minuses, right? And if I want to be real proper, I'll put in the states AQ for the ions and then solid for the reactants. All right, so the expression for the KSP is going to be the concentration of the product. So the concentration of Ce plus 4 times the concentration of IO4 minus to the 4th power because of the 4 right there. So now we got to figure out, well, what are the concentrations of these ions? They told us the solubility of the salt, so let's start there. I'm going to convert that to a decimal. That 1.6 times 10 to the minus 2 is really 0.016 grams for every 100 milliliters. So now I want the molar concentration, right? That's what I need for this equation over here. So let me convert grams to moles. I'm going to do a little, hey, they even give us the formula weight, so I don't have to do any crazy math. I know that the formula weight is 903.72 grams for every 1 mole of CeIO4. So now I got my grams cancel out. I have moles over milliliters, but let me convert the milliliters. Well, I know that every 1,000 milliliters is 1 liter. So now I can cancel out milliliters. I end up with moles per liter, and when I do that, it's 1.77 times 10 to the minus 4 molar. So it's saying that I started with 1.77 times 10 to the minus 4, CeIO4, 4, and then I dissolved. So the concentration of Ce plus 4 is going to be the same because it's a 1-to-1. But this IO4 minus is 4 times as concentrated. So it's going to be 4 times that 1.77 times 10 to the minus 4. So when I plug it into the KSP expression, KSP is going to be equal to that 1.77 times 10 to minus 4 times Well, 4 times that for the IO4 minus. So 4 times 1.77 times 10 to the minus 4, which also gets raised to the 4th power. So now I pick up my handy dandy calculator, beep bop, boop, and I end up with 4.45 times 10 to the minus 17 as my answer. A little involved, I'll admit it. All right, number 5. What is the molar solubility of barium sulfate, BaSO4, and they give you the KSP in a 0.5 molar solution. So the way we're going to do this is let's write out the reaction. What's happening here? I start with barium sulfate solid. It dissolves to give me Ba plus 2 in solution, so it's aqueous, plus a single sulfate ion, SO4 minus 2, which is also in solution. So my K expression is going to be the concentration of Ba plus 2 times the concentration of SO4 minus 2. Both of them have a coefficient of 1, so the exponents are 1. There we go. They're telling me that the solution already has 0.5 molar SO4. So it's really saying, hey, if I dissolve one of these, I would get X amount, right? So the concentration of barium in solution is going to be X, some amount. And my sulfate ion concentration is also going to be X, but it's going to be plus that 0.50 molar that is already in that solution. And that's got to equal my KSP. Now we're going to do a little trick here. I'm looking at KSP. It's a really tiny, tiny, tiny number. So I'm going to say, hey, when I do this X plus 0.5 molar, I know X is probably going to be really, really tiny. So when I add it to 0.5, I'm going to say, hey, that is still 0.50 molar. The concentration of that didn't change. Then we're going to check to see that we can do that assumption. So that simplifies things, right? I'm going to make that assumption. So my KSP, I'm saying, should be equal to X times 0.50 molar, because X is going to be really, really tiny. So if I add it to 0.50 molar, I'm going to assume I still end up with 0.50. So now I can just solve for X. I go, all right, KSP, they gave me the value. X I'm solving for. X equals, where'd I do this math? 3.0 times 10 to the minus 10 molar. And now I can check, hey, did that assumption work? Well, let me do 3.0 times 10 to the minus 10 plus 0.50. Hey, wait a minute. I know this is a significantly bigger number than that, so that's still going to give me, when I round to sig figs, 0.5 molar. So that check works out. If it didn't, you'd have to use the quadratic. All right, and I think I got a problem in here where you kind of got to do that, so I'm not going to work through it on this one. Number 6. Number 6, what is the solubility of calcium oxalate, right there, in a 0.08 molar calcium chloride at this? And they give us the KSP. So first step, write out what's actually happened. I'm starting with CaC2O4, and it's dissolving. It was a solid. It's dissolving to give me Ca plus 2 in an aqueous state, plus C2O4 minus 2 in an aqueous state. So my KSP expression is just going to be simply the concentration of calcium plus 2 ion times concentration of that oxalate, C2O4 minus 2. So that's my expression. So they're saying the solution is already 0.08 molar in calcium. So if I need to know the solubility of calcium oxalate, I know I'm going to really have X plus 0.08 molar as my calcium ion concentration, right? If X amount dissolves, I end up with X amount of calcium plus the 0.08 that was there, but I also end up with X amount of C2O4 minus, and that's got to equal my KSP. Now, let's do the quadratic approach. Let's say that when I add X to 0.08, I get a different number because they're equal in magnitude, they're similar. So then I distribute this X. I end up with X squared plus 0.08X has to equal KSP. So now I subtract KSP from each side. I get x squared plus 0.08x minus KSP equals 0. So now I can use my quadratic. My quadratic equation is, I think I wrote it down somewhere, right? It's negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is 1, my b is 0.08, and my c is negative KSP. So now I can just plug all those in, and I'm going to get only one answer that makes sense. I get x equals 2.88 times 10 to the minus 8. All right, so yeah, there you go. All right, number 7, what is the KSP for PbF2 if the molar solubility is 1.5 times 10 to the minus 3 molar? So I'm going to start with, just right now, what's happening. I start with PbF2 in the solid state, and it dissolves. So I'm going to get a Pb plus 2 ion in solution and 2 fluoride ion in solution. So my KSP expression is going to be, all right, products, I got lead ion, Pb plus 2 to the 1 power times the concentration of the fluoride ion, and it's going to get squared. And then the reactants are solid, so they're not involved. Now, the molar solubility is like, hey, I dissolved X amount of moles of PbF2, so I end up with X amount of Pb plus 2 ion and 2X of the fluoride ion, where X equals the molar solubility, which they told me is this number. Now, I'm not gonna, yeah, I guess I will. This is what we'll do. They want to know what is KSP. Well, we know we're gonna end up with X amount of Pb plus 2, and we're gonna end up with 2X amount of the fluoride ion, which is gonna get squared. So if I want to do a little math first, 2x in parentheses getting squared gives me 4x squared, which is still times by x. So I end up with 4x cubed has to equal my KSP, again, where the x is my molar solubility. So I get 4 times by 1.5 times 10 to the minus 3, and that value is going to get cubed. So when I plug and chug and get the answer for that, I end up with 1.35 times 10 to the minus 8 molar. Or no, I'm sorry, unitless. So yeah, that's how you do that. I hope you found it helpful. See you in class. Okay, bye.